Hello, this is Group 7. I'm Aiden,
I'm Joe.
I'm Reed.
and we did steel, aluminum, and brass. All right, I'm covering steel. This slide is talking about differences between elastic and plastic portions of a stress strain graph. The elastic portion is where the graph is linear, which for our graph goes up into, or from 0 to about 150 on the y, which is the stress, and then from 0 to about 0.2% on the x, which is the elongation. These values are a little bit lower than what you would normally expect from steel, which we're not entirely too sure why. This slide talks about the Young's modulus. So the Young's modulus is just the slope of the elastic portion of the graph, which for us is just determined by doing roughly 150, or our exact point was around 144, over the roughly 0.2 elongation, which yielded 855.62. This is in terms of megapascals over percentage. So if we wanted to convert that into gigapascals, we'd have to multiply by 100 and divide by 1,000, which yields about 85.562 gigapascals. This Young's modulus is what we got for steel, which is about 2 times less than what you would expect, which again, we're not really too sure how we got that. Here we're talking about the yield point. So the yield point is pretty simple. It's just where the graph switches from elastic to plastic. And for us, that ended up being around 155 megapascals. And that's just determined by finding where it switches from linear to being more curved, which it seems to be more of a logarithmic shape. And all that means is that the material starts going past the point of no return pretty much, where once you release it, it's not going to return to the original shape. And for the tensile stress is simply defined as the maximum stress a material can maintain before it starts to weaken, or just where the material starts to have less stress and still keep elongating. Which that can simply be found by finding the highest point. And for us, that ended up being around 270.58, which was solved for just by using a max function on the data that we had gathered. This slide covers ductility and reduction of area. These two factors are related in the sense that as one is more ductile, it means it's going to elongate more, and that just means that the area is going to reduce more. So to find the ductility, it's simply just the total percent elongation. So, or well, total percent elongation before it snaps. So in our case, that's around 44%. And to do the reduction of area, it's just you find the connection between the reduction of area and the elongation, and then you just plug it in. So for our case, we got a reduction of area of around 0.306. And for resilience and toughness, resilience is just the total area under the elastic portion of the curve, which can be found using an integral or just finding the shape, which is typically a triangle, so it'd be 1/2 base times height. And then toughness is defined just as the area under the entirety of the curve, which is just the total amount of energy the metal can take before it ends up breaking. Resilience is just the amount of energy a material can store before it becomes plastic. So you can think of it as like the spring constant. So a metal is springy in nature until it passes the resilience. And then yeah.
All right, so I covered aluminum. Young's modulus is defined as stress over strain. So I took the linear portion of our data and I graphed it in Excel with units of stress in megapascals and strain in percentile. So if we wanted to convert this right here from megapascals to gigapascals, we'd have to divide it by our percentile and multiply it by 1,000 to go from mega to giga, which would give us a Young's modulus of about 71, which is what you would expect for aluminum. Yield point is defined as when a material goes from elastic deformation to plastic deformation. During elastic deformation, the material will return to its original shape. During plastic deformation, it will no longer return to its original shape. Graphically, that looks like where your curve goes from a linear line to a non-linear curve. For us, that happened at about 225 megapascals, which is in the normal range for aluminum. Tensile stress is the maximum stress a material can take before failure. I've graphed an excerpt from our larger graph from where you can see it hits an absolute peak at around 312 megapascals. This is a part of a much larger graph where you would see it slowly starts to decline after this point, but it does not immediately break at that point. Ductility is a material's ability to stretch when plastic deformation is taking place. Think of gum being stretched before breaking. Percent elongation is how far the material stretches before breaking, which is measured by final length minus initial length divided by initial length times 100%. Percent reduction in area is how much the cross-sectional area of the material decreases, which similarly is modeled by final area minus initial area over initial area times 100%. Resilience is the area underneath the elastic part of the curve. This value can be thought of as how much energy a material can store before permanent deformation takes place. Think of a rubber band and how much it stretches before permanently deforming. Toughness is the area under the entire curve, and this is a measure of how much energy it takes to completely break a material.
Hello everybody, I'm Joe and I'm covering brass. We did not get to test brass in the lab, which means I had to get all of the data for the properties that make up brass from the internet. All the sources for each property can be found in the bottom right hand corner of each slide. Young's modulus, or Young's modulus of elasticity, represents the area, the slope of the linear part or more linear part of the stress strain graph. As we can see here, it's not perfectly linear, but it is pretty close to. It is calculated by taking the stress divided by the strain during that period. Brass can range anywhere from 75.8 gigapascals to 121 gigapascals, with an average value being around 105. The yield point is the point on the graph in which it transfers from its more linear state to a non-linear state, like more of a curve, and then flattens out, as we'll examine later. That is around this point of the graph I found, which the brass typically finds itself, its yield point being somewhere around 0.345 gigapascals up to 6.83 gigapascals, with its average being around 2.53 gigapascals. The tensile stress, or the ultimate tensile strength, is the highest amount of stress a specimen can handle before reaching failure. Brass typically has its ultimate tensile strength landing between 0.207 to 1.03 gigapascals, an average being around 0.4 gigapascals. Ours is around 0.45 gigapascals, so right there in that sweet spot. Ductility. Ductility is how much the specimen stretches or elongation, and how much does the cross-sectional area decrease compared to its starting values. In the data that I found that came with the graph, it did not supply me with any dimensions or elongation, so I was not able to calculate this myself for the graph, but the ductility typically for brass involves from 1% to 68% elongation, and 40 to 60% reduction in area. The averages being about a 28.8% elongation and 52.4% reduction in area. Toughness is described as the area under the elastic part of the curve, which can be calculated using triangles or trapezoids to simplify the shape and get our toughness. The toughness range for brass is anywhere between 0.3 to 0.86 gigapascals times meters. In this clip that we were provided, we see Spider-Man using his silk to attach one side of the ferry to another to try to hold it together so all the people inside don't die. As we also see, a few moments after this still was taken, the silk started to snap after quite a lot of load was applied to them, because the average weight of a ferry of this size is in the above 5 million pounds. And it stretched a little bit, had a little bit of elongation, and then totally its ultimate strength was reached and it snapped. So somehow Peter Parker's got to make that stronger, or next time he won't be so lucky and have someone save his butt.